In this presentation, we are going to look at the normal distribution. So the first thing we're going to talk about is the importance of it. Now, it's perhaps the most widely used distribution, and some would say it is overly used a bit too much, and sometimes it's used where it should not be used. A very interesting topic and something we'll return to. But it also is an underlying assumption for many statistical procedures. That is to say that a data set, when you're performing a particular statistical analysis, the data set that you are analyzing is normally distributed. Now, an important matter to look at in the short term, in the media right now, is the bell curve. And essentially, the normal distributions have the same general shape, and we call this shape the bell curve. And they are symmetric with scores concentrated in the middle around the mean. So this is the bell shape, the bell curve, and you could tell pretty quickly why it's called the bell curve, because this is the general shape. It's sort of like that. Okay. Now, the idea of the bell curve, essentially the height represents, at a particular point, represents how likely a value is to be. So this is the mean. And what it sort of says here is that the mean value is the most likely value to occur. Okay. Whereas a value near the mean, this is, let's say, near the mean, the height there, it means it's quite likely to occur. Likewise in this side. Whereas if you're far away from the mean, the height of the bell curve is very low. So that means a value at that far away from the mean is not particularly likely to occur. So again, most of the, we're going to call this shaded area here. We're going to look at that area. That's most of the values around the mean, and again, that area there takes up quite a lot. That shaded area there takes up quite a lot of the area under the bell curve. Whereas this area here, values that are far away from the mean, like this shaded blue area here, is not particularly large at all. So moving on, I'm going to go to the next slide here. So essentially that is the general gist of it. Now there's I've just tried to shoehorn quite a lot into that already. So what I'm going to do now is sort of consolidate a few of those points bit by bit. And that's a histogram. So that, this is a sort of an experiment. It's useful, and it's an experiment. It's a sort of oops, gone too far there. It's something I've discussed previously, or in other examples. It's not really important right now what it is, other than the fact it's a histogram, and it's a histogram with quite a lot of class intervals, quite a lot of bins, and it's also a really high number of values. And essentially, what happens is that here it's 100,000. So what happens is that once you have a really, really large number of values and numbers of observations, and you have really small bin widths, or smaller and smaller bin widths, you can sort of see the bell shape start to emerge there, just like this. There we go. So that's why it would be used quite a lot. Now, let's talk about some important matters here. The probability density function, which is the height of the bell curve at a particular point, okay, is mathematically defined in terms of two important parameters. The mean, I'm going to call this the normal mean, just to emphasize what I'm talking about later on, and the normal standard deviation. Okay, and these are denoted with the Greek letters mu and sigma. So it's really useful to get used to those. And again, you would reference them as mu and sigma. Okay, so I've got a bit crazy there with the marker. So, moving on from that, so mu and sigma So a normally distributed random variable would be denoted as follows. So this is something we might see at the top of an exam question. And so we would sort of say a random variable x is normally distributed with mean mu, and we'd actually, in this case, it's sort of conventional to write in the variance, which is the standard deviation squared. So for example, you might say something like this: x, let's say, is heights of something or other with a normal distribution, let's say 1.75 meters and 0.03 centimeters squared. It's actually, sometimes a lot of people would actually write in the standard deviation value and then just put in a square there just to sort of make it easier to follow. So that's how, and the norm mu is 175 and sigma squared is 0.03 to be squared. And these values here are vital for all the calculations that one would use when carrying out a standard a normal distribution question. So again, watch out for that banana skin. The convention here is to write with variance here and then deduce what the standard deviation is. So now this is the probability density function of the normal distribution. So this is a very impressive looking mathematical equation. And integrating this formula would allow us to compute a lot of useful probabilities here. So for example, if we were to go something like this, let's say from mu to 0, if you're familiar with that, even if you are familiar with that, that's actually quite a tricky calculation. So you don't actually use this formula at all, but it is actually important to know what a probability density function is. So you might actually see it in a lot of your statistical tables actually. Now, essentially what it is here, what that equation does is, for example, -1, if you were to put in -1 here, x equals -1, it would tell you the height of the curve at a particular point. So it'd be something like, let's say f of -1 is approximately equal to 0.27, something like that. I'm just guessing that's around 0.27. Okay, so that's what that mathematical function tells us, but again, it's not actually necessary to compute it. Now, the highest point, so these are the characteristics of the normal probability distribution, and a few of these are quite important. The highest point of the normal curve is at the mean, which is also the median and the mode. And as I sort of said previously, the normal mean is one of the two key parameter values. So for most of the time, you will be talking about the mean, and like very rarely use the median and the mode. Now this next one is important. I sort of stated this previously, but I'll sort of make more emphasis here that it's bell-shaped and symmetric. So symmetric is an important matter, with the shape of the curve to the left of the mean a mirror image of the shape of the curve to the right of the mean. Now the reason why this is very important is because this particular point here, the second point here, underlines a very important rule for dealing with the probability, the normal probability distribution, and that rule is called the symmetry rule. And it's how you would deal with negative values. It is, again, the symmetry rule is actually so important, it's actually worth its own presentation. So look out for that. Anyway, what I was going to say here is that pretty much if you were to sort of draw a line from here down to there, essentially what is to the left of the mean and to the right of the mean is the mirror image of each other. That would be to say that this shaded area down here, which starts at -2 and works left, is the mirror image, with this being the axis, the line of the mean, with that being the mirror image, those two blue shaded areas being the mirror image of each other. Quite an important little matter, that. Okay, and again, the mean is the highest point there. That's point 1. So I got 2 more of those. The standard deviation, it determines the width of the curve. Larger values of standard deviation result in wider, flatter curves, showing more dispersion in the data. Okay, that's quite important. So if you had a low standard deviation, your curve would look something like this. And if you had high standard deviation, your curve might look something more like that. Sort of, if they were to be compared side by side. That's not really a very good bell curve, but you get the idea. The total area under the curve for normal probability distribution is 1. Okay, so that's actually also an important matter. Let's go back here, that the total area under this curve from minus infinity to infinity, the total area under the curve is considered to be 1. That's a sort of important matter. It's why you're able to represent probability with curves. The enclosed area has to be equal to 1. Okay, let's move on from that. Now, this is a couple of important remarks. Now, you're not exactly, it's not absolutely necessary to prove them, but they do come in useful. So this is the shaded area. I'll just make it a little bit clearer. This is minus 1 here, and this is 1. Okay, and these are the denomination of the axis here is in terms of standard deviation. So this is the mean value here, and I'm going to call that 0, and this is minus 1. So this is 1 standard deviation to the left, this line here. And this is 1 standard deviation to the right. And the point of this is that you probably might not be able to make that out, but essentially, as I sort of said previously, the total area under the curve is 1. This, between minus 1 and 1 standard deviations away from the mean, this accounts for around 68% of the curve. Okay, and leaving 16% in both tails. So there's 16 in this tail and 16 in this tail. Okay. Now, it's not, these values, I don't like telling people to memorize things, but you should be able to do these calculations from first principles. I come up with that 68% and 16% and so on. But it is handy to know them off by heart. There's a couple of numbers that are handy to know off by heart, and that would be one of them. And in many cases, in an exam situation, you would not be required to sort of justify your answer of 68% from something like that. Here's another one. So I've done plus or minus 1 standard deviations. This is 1.96 standard deviations away. So this is 1.96 standard minus 1.96. So this is 1.96 standard deviations away from the mean in this direction. This is 1.96 standard deviations from the mean in this direction. Okay. And between the shaded area between those two bounds, minus 1.96 standard deviations and plus 1.96, this equates to 95% of the total area under the curve. It's not particularly evident there. It's this area down here will correspond to 2.5%, and this area down here, these tails, that also corresponds to 2.5%. So this tail here, 2.5%, and this tail here, also 2.5%. Later on, you will start to see this number 1.96 come up quite a lot, and in particular, its connection to 95%. One more, and this is it's another very similar remark to the one I've just made. It is 2.58. The mean plus or minus 2.58 standard deviations away. Again, 99% is actually 99.01. And again, between between here, between here, minus 2.58 standard deviations, and here 2.58 standard deviations. That being the mean. This accounts for 99% of the area under the curve. Okay. And leaving 0.5% in each tail. Okay, actually, when you're dealing with these values, watch out for this percentage here. That's equal to 0.005. Okay, okay, and not equal to 0.05. That's a common mistake people make in exam situations. This is around 5%. The blue one here. This is in red. That's about 0.5%. Very big difference between the two. Moving on. So, this is a very important one. This is called the standard normal distribution. Okay. Now, I am going to give this a different. I'm going to call this the Z distribution, and the reason for that is to sort of emphasize it as a special distribution in its own right. So you would have the normal distribution, and you would have the standard normal distribution. But just for the sake of clarity, I'm actually going to call it the Z distribution just to emphasize the difference as much as I can between the two. Now, it is a normal distribution with mean of mu equals 0 and standard deviation is equal to 1. That is always the case. They never change. With the Z distribution, the mean is always 0 and the standard deviation is always 1. Okay? The X, it's commonly given the letter Z to represent it to emphasize the difference between X. Now, the reason X is used is like X is just a generic name for a random variable. It's a generic symbol for any random variable, so it can mean anything. Like you might in X, like X might mean something else when we're dealing with the binomial distribution. But Z or Z has a very specific meaning, so it's sort of reserved. Now, just as another remark, the reason this distribution is so important is because it is well described in statistical tables. So when you're doing this in exam, in many situations, you will be given a statistical tables with the standard normal distribution, the Z distribution, tabulated. So when you look at these tables, you'll be able to deduce values from the for the Z distribution. One particular example, in the one that is used in the university I work in, is the Murdoch-Barnes tables. But there's other types as well. Actually, just as a quick remark, there are other types of tables, and they work slightly differently to the Murdoch-Barnes. So it's worth looking at that later on. And okay, so rather than computing probabilities from first principles using the integral formula presented earlier, which is very difficult, probabilities from distribution other than the Z distribution, for example, this here, X, let's say X is a normally distributed random variable with mean equal to 100, let's say 100 kilograms, and variance equal the variance is equal to 16. Actually, just to sort of emphasize a mishap that some people might do, the standard deviation in this case is 4. That's just a sort of little aside. And these can be computed using the Z distribution, which is a much easier approach. Now, we're going to demonstrate this approach shortly, okay? So, let's move on. Essentially what you do is you will come up with an equivalent value from the Z distribution and look up the probability for that Z value. So this is what I was talking about here. All normally distributed random variables have corresponding Z values, and we're going to call them Z scores. Okay, so this is quite an important matter. This is actually how you would compute a probability associated with a normally distributed random variable. Now, for normally distributed random variables, the Z score can be computed using this formula here. This is quite an important formula here. It is the standardization formula. So it's how you find the Z score. The little subscripts there just indicate observed values. Okay, it's an observation from the underlying X distribution. And Z0 is the Z score that corresponds to X0 or XO. Now, this is the mean of the standard. For example, in dealing with the one, let's using the example I've used previously on the last slide, we would sort of say this is the mean of the standard. This is the mean of the normal distribution and the variance, the standard deviation of the normal distribution. Just going back where I had 100, so we write something like that. Okay. Just to sort of go back to the last slide where that came from, that 100 and these two values here, 104. Okay. Whoop, it's gone off the page there. There we go. So moving on to the next slide. It'll actually adjust for me. And I have to edit this bit out. There we go. Sorry, just as a quick remark, terms with subscripts mean particular values and are not variable names. That's just from the last slide. It's just like anytime I put a subscript in, it just means it's a particular value, like 1.96. Now, importantly, probabilities relating to the Z distribution are comprehensively tabulated in statistical tables, such as the Murdoch-Barnes Table 3. And the way these tables operate is quite important. For the Murdoch-Barnes, will actually so for some value k, what the Murdoch-Barnes probability distribution will give you this. The Murdoch-Barnes tables will give you this value here, probability of Z greater than or equal to k. And the other statistical tables can be used, but they will tabulate probabilities in a slightly different way. I'm going to do sort of one presentation for working with the Murdoch-Barnes and another presentation working with a different type of table. So I'm going to sort of keep that as a separate presentation. Now, if two values and Z0 and X0 are related in the following way for some values mu and sigma. Essentially, Z0 is the Z-score of X0. Then we can say this. The probability of X being greater than X0 is equal to the probability of Z being greater or equal to Z0. Now, X, let's say, could be height. So this could, like, X is height. So that could mean the probability of X being greater than 1.82 meters or something like that. And that could be equal to the probability of Z being greater than 2, let's say. This is an identity we could use. Now the reason we could, this is the using the complement. This is just the complement approach there. So these are just the complements of this line here is just the complements of those. So what about this? Now this is usually what you're asked. This is usually what you're asked in a question, something like this. What is the probability of a height being greater than 1.82 meters? And what you do is you use the standardization formula to find out the Z-score, and then you will actually have an expression like this. So suppose the Z-score is 2, then you will be able to sort of say, well, this probability of X greater than 1.82 is equal to probability of Z being greater than 2. And this is something you can look up in the tables, this particular value here. And this actually works out to be 0.0225. Okay. So what you could sort of say in that case is, if this is equal to this, and this is equal to this, then X greater than 0.1, greater than or equal to 0.128 is equal to 0.025. So this is something you can look up in the tables, a value like this. Very simple job. And then you have your answer to your question. Okay. So it's a fundamental fundamental to solving problems involving normal distributions. I'm going to leave it there. The couple of other matters that I've raised are best dealt with in other presentations.